In the last module, we talked about that how we can calculate natural frequency for different systems, and we have gone through few cases in which damping was involved, uh, and we gone through different system which based on their classification was like overdamped and critically damped, right? These two systems we have discussed, and also there is a distinction parameter which makes difference between these two things. It was Chi, which is known as damping factor, right? Now the condition we generated from this damping factor, if our Chi, which is the ratio of uh, damping to the critical damping, is greater than 1, is said to be, the system is said to be in the state of uh, overdamp, right? And similarly, if psi is equal to 1, it is known as critical damping. Now we are going to discuss third case in which psi is less than 1, right? Which certainly signifies the case of the system is in a state of being under damped, right? Now, solving the differential equation we discussed previously, and we have gone into we calculated its solution as well, and now we are analyzing by putting different values of psi. We had used the case where chi is greater than 1, chi is equal to 1. Now this is the case where chi is less than 1. So this differential equation will have the solution in the form, right, which is x equal to a2 here is the constant, e to the power minus xi omega and t, right? And this is sine 1 under root 1 minus xi square omega and t plus phi, right? Where phi is the phase difference and omega is the natural frequency, chi, as we know, that damping factor, and it was the constant. Now this relation will explain us that how the amplitude of the system is going to get decreased and how much time it will take, and because this amplitude is function of time, as we can see that term t is involved. And another thing we can conclude from this solution is that this term involves this sine function as well as exponential function, right? If we try to draw it, we can see that e has a negative power, right? And if you plot the sine curve, it will like this. Just for the sake of explanation, we can make it like this, and certainly it is going to get decreased, so the amplitude is going to get vanished as the time processes ahead. We can see that this decrement, we can match the top of this curve. We could see that this exponential curve is going to get vanished as time goes ahead, and we can say at somewhere t is equal to infinity, the system is going to be going to come at rest, right? So this is how it is different. Now if we say if we compare the solution of overdamped system, it is certainly reflect that in that part also our system is going to come into rest by this the same mode of exponential function, because exponential function was involved in the solution of overdamped system as well, but it was consist with only exponential solution. Now comparing with this state of being underdamped, this function involves exponential as well as sine function. So this is going to get decreased very smoothly, and there is no hampering in the system. This is what we are going to suggest. Now look at in a brief way its practical application. If we are making system overdamped, right, it certainly has some vibration, and we are trying to neutralize those vibration. And if we put our system in the state of being overdamped, its amplitude of vibration will certainly, you know I mean, very fast will come down to neutralized compared to underdamped system. Here we can see that sinusoidal wave is going to get decreased very slowly as time goes ahead, and it will take a little more time compared to overdamped system to come to at rest. Right now, there is one important thing which involves here is that how one more thing I would like to firstly clarify about the critical damping case and the discussion that how we can categorize the periodic motion and aperiodic motion, right? If you remember the solution of the first case, which is overdamped, this says x is equal to c1 e to the power something here, and similarly c2 e to the power something like this, right? If I'm saying that this system is going to come down to equilibrium very fast, so it represents something this kind of case, and it will be become zero at somewhere t equal to infinity, right? So if we just look into the graph of it, right, if you just look into the graph of it, this system is not a periodic motion. The system is not a periodic motion. Similarly, this part here represent a periodic motion, right? Now, what is the separating line between these two sort of motion, right? This is a aperiodic motion, we can say. Now, what is the separating line between these two? This is the separating line between these two. Now, if we are saying that system is in aperiodic motion for overdamped system, so critical damping is the dividing line when system turn out from aperiodic to periodic, right? Now, one more conclusion we can draw out here is, if you are saying that system is overdamped, that means we have higher amount of uh, damping is higher, right? If damping is higher, the response of the system is very sluggish, right? This is what we need to keep in our mind. And indeed, if we remove the factor of these deriving equation mathematical calculation, we can see that if damping is higher, system is going to come down to its equilibrium state very soon, right? So these are the few terms that we need to understand in terms of while we are talking about free vibration, right? Now, if we say that the if a small amount of damping, you know, uh, damping is capable enough to bring the system in equilibrium with a infinite time, right? But in practical situation, this is not the condition, and this is not desirable as well. So we are looking for some finite value. So this fact is crucial to the importance of damping in a vibrating system under resonant condition. We will take few example in this regard to discuss it more broadly, right? Now, there is one another theoretical term of this chapter which is generally used. It is about the logarithmic decrement, right? Now, this is generally the ratio of two successive implodes. Now, I'll draw again the curve of underdamped system. This was the case. This is how it is going to get decreased, right? So this is how it is decreasing as I had drawn it previously with respect to time and amplitude. Now, so this logarithmic decrement generally represent the ratio of two successive amplitudes, right? We can say it like that. This is our XA, this is XB, this is XC, this is XD, XE. Namely, this shows the situation of A, B, C, D, E, and so on. Now, so the formula which comes out after that, I mean, as it is clear that this is the ratio of successive amplitude at its for an underdamped system. This particular point need to be underlined. This is for this case is only for underdamped system, right? Because we drawn the graph for critical damping and over damping, it's shown a it showed a steep decline in amplitude, right? So there is no periodic in that sense, so there is no concept of successive amplitudes like that, right? Now, for in this particular case of logarithmic decrement is for under underdamped case only, logarithmic decrement, right? This is what we need to keep in our mind here. Okay, now we are not again going into the depth of derivation, but we try to get some information that why we are discussing it. This is what our focus, as I said in the starting of the lecture, that this is what our focus, this is what our focus for the entire chapter, that how we can use the concept, right? And this first module is only based on the theoretical concepts, right? Not just formula, not just numericals, but a thorough, detailed explanation that how we can put these things in use, and slowly we'll move ahead and narrow down our discussion towards that how we are concluding these theoretical concepts to get some use it in use these concepts in terms of designing and maintenance. Now, so this XA upon XB is comes down to in logarithmic term, right? This is log e base, as I explained earlier. That is why it comes out to be, if you derive it, the ratio of amplitude will come out as a logarithmic term. So therefore, this ln is involved, and hence the name of this uh, formula. It it solely depend upon the damping factor of the system, right? Minus xi square, right? So this is so far the formula. Now this formula is for successive amplitude, right? Suppose that means this is for XA and this is having XB amplitude. Now if we are if we have need to calculate the ratio of these two amplitudes, right, we can clearly see that this decrement in the sine curve amplitude goes down exponentially. This is what we have seen in the equation as well. Now, suppose from here to here, come down here, it has gone through n cycles. Now, the formula to calculate the logarithmic decrement here is 1 by n ln. Suppose, let's say this is the initial and this is the nth uh, amplitude. So this is what the formula. We don't have to go successively, but we can take the initial amplitude and the final amplitude, and this will also help us to calculate. One more thing, there is one more concept that will come in picture for underdamped case, which is the concept of damped natural frequency, right? Why it has come into picture? Because we are using underdamped system. So this represent omega d is equal to under root 1 minus xi square into omega n, right? So this is just a formula that if you are dealing with the underdamped case, we will certainly go down to damped natural frequency, which again the function of damping factor, and it represents the amount of damping present in the system uh, would bring down the system's frequency from the low from the natural frequency. So this is what the case, and we as an engineer and designer, we are required that our damped natural frequency should not matches up with the natural frequency, as we had a broad discussion over it with the help of numericals and so on in the previous lecture. Now let us take a example of a uh, of a real life problem. I mean, it's not that much broad, but it will give you some sense surely. Now let us see that here is an example. Suppose there is a gun barrel, right? That we all know that dealing with the guns is a general case of vibration that everybody has seen, right? Now, let us say that gun barrel has a mass of around 600 kg, right? And the spring which performs the function of recoiling, it has a stiffness of K is equal to 294,000 Newton per meter. Now, if the barrel recoils 1.3 meters on firing, right? This is the this is what your amplitude in that case. If the barrel recoils 1.3 meter in firing, so we need to, if we need to determine the initial velocity. If we see the basic gun's structure, right? I am making a rough diagram here, right? So we press the trigger right here, and this has a spring and it fires the bullet. Let us say we compress it, right? And in the sense of recoiling, it goes backside by 1.3 meter and spring has this stiffness, right? Recoiling gives the bullet speed, and it releases from inside the barrel, and we need to calculate this recoil velocity, right? So here we can see the energy stored in the spring. For the calculation of natural frequency, we have seen it is half kx square, right? Now this stored energy within the spring ultimately releases to the bullet and gives it the initial velocity v naught. Now with the help of this energy conservation method, we can see that half kx square is equal to half mass of bullet m v naught square, right? So by putting these value, we can get the value of v naught, right? My task is not here to make you understand about uh, the numerical calculation, but I am trying to, you know, combine those concepts that we have learned earlier. Now, if we have to calculate the critical damping amount of this case, right? If you remember the formula, we had there Cc is equal to 2 under root K M. Now this critical damping shows that we can put the value of K and put the value of M. Here we got the C value, right? Similarly, we can calculate the natural frequency for this problem. This is a omega n is equal to under root K upon M, right? So these are all the things that we can relate to a particular bullet case, as we just see in this lecture. Now let us see one more case which shows the part of this logarithmic decrement kind of thing, right? If let us say a disk, take an example of this. I hope this one is clear for you, the guns example. Now the a torsional pendulum, right? If you go through the numericals, you will see that there are such sort of uh, cases, right? Now we can see that torsional pendulum, I'm just taking a normal example, not the broad one here. If a torsional pendulum is successively having uh, amplitude of 9 degree, 6 degree and 4 degree, right? So we need to calculate the logarithmic decrement, as I said earlier. Now how we can calculate it? So here we have successive amplitudes A, B and C. So if we say delta is equal to ln 9 by 6, it has similar value for ln 6 by 4. Now if we need to calculate the cycles, if we have this initial initial and final amplitude, and we don't know that how much cycles the system has gone through to get rid of that vibrational phenomena, so we can have here is 1 by n ln x naught by xn, right? In case we are having the initial and somewhere here the final amplitude, and we have this amount of logarithmic decrement, so we can go through. Now using this logarithmic decrement amount, we can calculate our damping factor from this equation, right? Which is this damping factor is very crucial for designing of any system on the basis of vibrational aspects, right? You can go through multiple formulas to calculate the values. Now, since we are talking about the torsional pendulum, so this is a new case where torque has more involvement to calculate the natural frequency of the system, stiffness, and other values. So I would like to take this discussion towards the torsion cases. Now, if we calculate critical damping in the situation, in the previously I told you the formula would be under root 2 under root km. For this case, this is 2 under root the torsional stiffness. That is why I am representing it with kT and the polar moment of inertia. Right? I hope you are familiar with the polar moment of inertia concept. Right? It is always the perpendicular axis. Right? Inertia about this perpendicular axis. We are certain about the moment of inertia about the x-axis, y-axis, and the third axis, which is z-axis. If you are calculating the moment of inertia about this z-axis, we can get this moment of inertia with the help of perpendicular axis, which is I xx summation of the moment of inertia about another two axes. Now the important formula for torsional case is this one. Now how to get this torsional stiffness? If we look into the formula, I hope you have read in this in the subject of strength of material, which shows torsion equation is T upon J is equal to tau upon r is equal to g theta upon L. Now, for this case, for in journal, when we were discussing spring in previous part, we said that the stiffness, the basic formula of a spring is given by F is equal to kx, and in order to calculate this k, we have the ratio F by X. That means F is the force which has involvement of stretching that spring, and X is the resultant that we got from there. Now, for this case, the load is in the form of torque, and the displacement or amplitude we are getting in the form of this angle theta, right? And this now the ratio of T by theta will represent this KT, right? So here we get Gj divided by L as our formula here, right? So this is the case where torsional stiffness we can calculate from this torsion equation. Now one thing is quite clear from here, that we are trying to get the stiffness first, right? It has been the first case we have been discussing. Now we need to keep in our mind those basic definitions and try to put these concepts more ahead to calculate our requirement for designing purpose, right? This is stiffness, damping factor, critical damping, and in the next lecture we will develop few more concept and analysis based talk, that how we can determine the system is in safe condition or not, right? So this is what we are going to discuss in our next lecture. Thank you very much.